I welcome you all to my lecture number 11 on signals and systems for electronics and communication engineering students and for electronics and computer engineering students. Today I am going to discuss continuous time Fourier transform, that is Ctft. An aperiodic signal can be viewed as a periodic signal with an infinite period. This is very important. I repeat, an aperiodic signal can be viewed as a periodic signal with an infinite period. More precisely, in the Fourier series representation of a periodic signal, as the period increases, the fundamental frequency decreases and the harmonically related components become closer in frequency. As the period becomes infinite, the frequency components form a continuum and the Fourier series sum becomes an integral. Now we will go for development of the Fourier transform representation of an aperiodic signal. So for that, I'm going to consider a continuous time periodic square wave xt as shown on the screen. Now the basic pattern in xt is this, and this pattern repeats itself after a duration of capital T. So this makes xt periodic. Now specifically over one period, we define x cap t is equal to 1 for magnitude small t less than capital T1 and x cap t is equal to 0 for magnitude t lying in the range capital T1 to capital T by 2. Mark it as equation A1, and now I have plotted x cap t here. X cap t is having amplitude 1 when t is lying in the range minus capital T1 to capital T1. However, the total period is from minus capital T by 2 to capital T by 2 as shown on the screen. Now, x cap t periodically repeats with period capital T in xt as shown in above figure. The Fourier series coefficients of this square wave, that is ak, are as represented in equation A2, which we have derived in last lecture. Ak is equal to 2 sine bracket k capital omega naught capital T1 divided by k capital omega naught capital T. Mark it as equation A2, where capital omega naught is equal to 2 pi by capital T. An alternative way of interpreting equation A2 is as samples of an envelope function, specifically capital T ak is equal to 2 sine bracket capital omega into capital T1 divided by capital omega, where capital omega is equal to k capital omega naught. Mark it as equation A3. Now we know that sinc x is equal to sine bracket pi x by pi x. This is the definition. Now, using this definition, I can rewrite equation A3 as capital T ak is equal to 2 capital T1 sinc bracket capital omega capital T1 divided by pi, where capital omega is equal to k into capital omega naught. Mark it as equation A4. Now A4 is represented in terms of sinc function, with capital omega thought of as a continuous variable. The function 2 sine bracket omega into capital T1 divided by omega represents the envelope of capital Tak, and the coefficients ak are simply equally spaced samples of this envelope. Now I have plotted capital T AK with respect to capital omega for capital T is equal to 4T1. Now this green colored signal shows sinc function, and these points show the sample values. Now in the sinc function, because capital T is equal to 4 capital T1, therefore first null is observed at capital omega is equal to 2 capital omega naught and at minus 2 capital omega naught as indicated in the graph. Now as capital T increases, or equivalently as the fundamental frequency capital omega naught is equal to 2 pi by capital T decreases, the envelope is sampled with a closer and closer spacing. That is, if capital omega naught decreases, then the distance between these two sample points decreases. As capital T becomes arbitrarily large, the original periodic square wave approaches a rectangular pulse. That is, all that remains in the time domain is an aperiodic signal corresponding to one period of the square wave. I repeat, as capital T becomes arbitrarily large, the original periodic square wave approaches a rectangular pulse. That is, all that remains in the time domain is an aperiodic signal corresponding to one period of the square wave. Also, the Fourier series coefficients multiplied by capital T become more and more closely spaced samples of the envelope, so that in some sense the set of Fourier series coefficients approaches the envelope function as capital T tends to infinity. Now the Fourier series representation of xt is equal to summation k running from minus infinity to infinity ak e raised to power j k capital omega naught t, mark it as equation B1. And ak is equal to, that is Fourier series coefficients, ak is equal to 1 by capital T integration from minus capital T by 2 to capital T by 2 xt e raised to power minus jk capital omega naught t into dt, mark it as equation B2, where capital omega naught is equal to 2 pi by capital T. Now, since xt is equal to x cap t for magnitude t less than capital T by 2, and also since x cap t is equal to 0 outside this interval, equation B2 here can be rewritten as ak is equal to 1 by capital T integration from minus capital T by 2 to capital T by 2 x cap t e raised to minus jk capital omega naught t dt, mark it as equation B3 based on this. That is xt is equal to x cap t for magnitude t less than t by 2. But we know that x cap t is 0 outside this interval. So I can write B3 as equation B3 as ak is equal to 1 by capital T integration from minus infinity to infinity x cap t e raised to power minus jk capital omega naught t into dt, mark it as B4. So I have incorporated this condition here in B4. So limits are from minus infinity to infinity. Therefore, defining envelope capital X cap j omega of capital T ak as capital X cap j omega is equal to integration from minus infinity to infinity x cap t e raised to minus j capital omega t dt, mark it as equation B5. However, ak is equal to 1 by capital T x cap bracket j k capital omega naught, mark it as equation B6. Now look at B4. So I can use B5 to represent AK as 1 by capital T X cap bracket JK capital omega naught. Now combining equation B1 and B6, look at this, B1. Now I will substitute the value of AK here. Now combining equations B1 and B6, we express xt in terms of x cap j omega as xt is equal to summation k running from minus infinity to infinity 1 by capital T x cap bracket jk omega naught into e raised to power jk omega naught t. Mark it as equation B7. But we know that capital omega naught is equal to 2 pi by t. So instead of 1 by t, I will substitute omega naught by 2 pi here. So xt is equal to 1 by 2 pi summation k running from minus infinity to infinity x capital X cap bracket j k capital omega naught into e raised to power j k capital omega naught t into omega naught is equation B8 as shown on the screen. As capital T tends to infinity, xt approaches x cap t. As capital T approaches infinity, xt approaches x cap t. Both will become same. Furthermore, capital omega naught tends to 0 as capital T tends to infinity. And the right hand side of equation B7 here, right hand side of equation B7 passes to an integral. Therefore, xt is equal to 1 by 2 pi integration from minus infinity to infinity x bracket j omega e raised to power j omega t d omega. Mark it as equation B9, which is based on equation B8. Omega naught is tending to 0. Capital T tends to infinity. Omega naught tends to 0. Similarly, capital X j omega is equal to integration from minus infinity to infinity xt e raised to minus j capital omega t dt. Mark it as equation B10. This is based on B5, equation B5. Look at this equation B5. So capital X j omega is equal to integration from minus infinity to infinity xt e raised to power minus j capital omega t dt. That is equation B10, which is based on equation B5. Now equation B9 and B10 are referred to as the Fourier transform pair. I repeat, equation B9 and B10 are referred to as the Fourier transform pair, with the function capital X j omega referred to as the Fourier transform or Fourier integral of xt in equation B10. And equation B9 is inverse Fourier transform equation or synthesis equation for aperiodic signals. Now, I repeat, the function capital X j omega referred to as the Fourier transform or Fourier integral of xt, and equation B9 is inverse Fourier transform equation or synthesis equation for aperiodic signals. So capital X j omega is the spectrum of xt. Next is convergence of Fourier transform. Let x cap t denote the signal obtained by using capital X j omega as x cap t is equal to 1 by 2 pi integration from minus infinity to infinity capital X j omega e raised to power j omega t d omega. Mark it as equation C1. When is x cap t a valid representation of the original signal xt? This is a question. if xt has finite energy, that is if it is square integrable, so that integration from minus infinity to infinity, magnitude xt square dt is less than infinity, mark it as equation C2, then we are guaranteed that capital X j omega is finite. And for aperiodic signals, integration from minus infinity to infinity, magnitude et square dt is equal to 0. Mark it as equation C3, where et is xt minus x cap t, that is error signal. Just as with periodic signal, there is an alternative set of conditions which are sufficient to ensure that x cap t is equal to xt for any t except at a discontinuity where it is equal to the average of the values on either side of the discontinuity. These conditions again refer to as the Dirichlet conditions, and it is required that xt be absolutely integrable, that is, integration from minus infinity to infinity, magnitude xt dt must be less than infinity, that is equation C4, and it is required that xt have a finite number of maxima and minima within any finite interval, and also it is required that xt have a finite number of discontinuities within any finite interval. Furthermore, each of these discontinuities must be finite. Therefore, absolutely integrable signals that are continuous or that have a finite number of discontinuities have Fourier transforms. Now, noteworthy point. It is noteworthy that periodic signals, which are neither absolutely integrable nor square integrable over an infinite interval, can be considered to have Fourier transform if impulse functions are permitted in the transform. I repeat, it is noteworthy that periodic signals, which are neither absolutely integrable nor square integrable over an infinite interval, can be considered to have Fourier transform if impulse functions are permitted in the transform. This has the advantage that Fourier series and Fourier transform can be incorporated into a common framework. Now consider first example. Consider the rectangular pulse in time domain. That is, consider the rectangular pulse signal in time domain as xt is equal to 1 for magnitude t less than capital T1 and xt is equal to 0 for magnitude t greater than T1. Mark it as J1. Now get the continuous time Fourier transform of xt. That is, we need to know capital X j omega. Now using the formula that capital X j omega is equal to integration from minus infinity to infinity xt e raised to minus j omega t dt is equal to integration from minus capital T1 to T1 1 e raised to power minus j omega t dt. This limit has changed to minus capital T1 to T1 because xt is having value 1 when small t magnitude is less than capital T1. Now opting the conventional integration procedure, I can get capital X j omega is equal to sine bracket capital omega capital T1 divided by capital omega. And that is equal to 2 sine bracket 2 pi capital F capital T1 divided by 2 pi capital F T1 as shown. Now we can express this in terms of sinc function, and we need to do this simplification. And that leads to equation J2 as capital X j omega is equal to 2 capital T1 sinc bracket capital omega capital T1 divided by pi. Now I have plotted capital X j omega with respect to omega. Here it is a sinc function, and the first null is obtained at capital omega is equal to pi by capital T1, and at capital omega is equal to minus pi by capital T1. And amplitude of the sinc function is 2 capital T1. Therefore, we can observe that the continuous time Fourier transform of a rectangular pulse in time domain is a sinc function in frequency domain as shown. In next example, consider the signal xt whose Fourier transform is capital Xj omega, and the capital Xj omega is equal to 1 for capital omega magnitude less than W, and capital Xj omega is equal to 0 for capital omega magnitude greater than W. Mark it as equation K1. Now get the continuous time inverse Fourier transform of capital Xj omega. That is, we need to know xt in time domain, continuous time domain. Now we have been given that in frequency domain, like in the previous example, there is a rectangular pulse in this question. We have been given that there is a rectangular pulse in the frequency domain. That is, Xj omega is equal to 1 for magnitude capital omega less than W, and Xj omega is equal to 0 for magnitude omega greater than W. So it is a rectangular pulse in frequency domain. Now we need to know xt. Now I am going to apply the formula for inverse continuous time Fourier transform. That is, xt is equal to 1 by 2 pi integration from minus W to W 1 e raised by j omega t d omega. Now this is based on this given condition, and simplifying it using the conventional integration procedure, I can get xt is equal to 1 by 2 pi bracket e raised power j tw minus e raised power minus j tw by jt, and that is equal to sine capital Wt by pi t. Now I can express xt in terms of sinc function as capital W by pi into sinc bracket capital Wt by pi. This is equation K2. Now I have plotted xt with respect to t, and this is a sinc function with amplitude capital W by pi, and we can observe that first null is appearing at t is equal to pi by capital W and at t is equal to minus pi by W. So this is sinc function. Now the observation is that the continuous time inverse Fourier transform of capital Xj omega is a sinc function in time domain. Now we will there is another important observation is that in this example we have considered a rectangular pulse in time domain, and when I have calculated its continuous time Fourier transform, its Ctft is a sinc function in frequency domain. Now in next question, here we have considered a rectangular pulse in frequency domain, and when I have calculated its continuous time inverse Fourier transform, then I have observed xt to be a sinc function in time domain. So this special relationship J1, J2 and K1, K2 that is apparent here is a direct consequence of duality property for the Fourier transforms. I repeat, the special relationship J1, J2 and K1, K2 that is apparent here is a direct consequence of duality property for the Fourier transform. And we will discuss this in the next lecture. Now, it is important to know that continuous time Fourier series representation is used for periodic signals only, whereas continuous time Fourier transform representation is used for periodic as well as aperiodic signals. So I finish my lecture here. Thanks for attending this lecture. These are some reference books. This is the main textbook, that is Signals and Systems by A.V. Oppenheim and by A.S. Wilsky and by S.H. Nawab. And you can take help of other reference books also, as shown on the screen. Thanks for attending this session on Signals and Systems. See you in next lecture. Have a nice day.